the feedback control system and its characteristics. All right. So when we say that we are looking at a feedback control system, our intention is to bring the concept of feedback from the output. You take up a part of the signal, pass it through a block called feedback. There will be some gain related to the feedback, and we give it to the summer block where you detect the errors. So in general, if we want to represent the feedback system in terms of a block, we will call it as a closed loop system. Okay, so feedback control system is also referred to as the closed loop systems. Okay, fine. Now let's try to build such system. So we need a block. This is where the input signal is taken in with respect to the system from the outside world. So this is called as the reference. So we were discussing that the input is taken into the system through a block called as the reference selector. That's the name. And this takes the input signal from the outside world. We call it as uh, the input command. The input command passes through the reference selector, and that generates a specific type of input to the system. This is called as the reference input. All right, then this will go to a specific it's a modulator. It's a product modulator, or in terms of a signal it actually subtracts one from the other. But anyway, right now we are not discussing about what type of feedback it is. So as of now, it's simply called as an error detector that actually gives a signal to the plant and produces the output. It generates output. Now this output is collected from here and then given it back to the feedback. It goes through this and given it back. Now this signal is called as the feedback signal. So the signal, the output of the error detector is called as the actuating signal. Right. So these are the general characteristics of a feedback control system. Right. What all the different parts it's going to have, we can see over here. Right. So each part, when it comes to a circuit which has the feedback, which is a feedback control system, right? Maybe reference selector could be a parallel resistor, right? And the plant could be the voltage, right? That gets converted from what's the input voltage to a double of that voltage doubler circuit, right? And we will have a variable resistor at some location which generates a part of the output to be produced at the input. Once again, that's a feedback, etc. So we can see that, right? So every feedback control system, right, that we try to build, maybe a circuit or maybe any other device, right, will be having these components in general. Okay, now comparing this with, right, okay, let's first write some example, then we'll go for the other type of control and we'll compare, right? So maybe the example could be the voltage uh, control of maybe a DC generator is example, right, in terms of a circuit, right, which we can build as a part of a closed loop system. Okay, and going to any mechanical part, you can say that the room heating system. So you measure a temperature continuously gets monitored for a given room, right, depending upon the present temperature and the set value, right. If there is a difference, you work, right, the heater will work, otherwise heater stays off. So you see that it's a on off control is decided by the feedback system. Okay, so like that we have we can give examples of the control system which have the feedback as a part of it. Okay, now let's try to compare. One very important comparison that comes into picture whenever we discuss about the feedback is that uh, what's the difference which has no feedback? That's called as an open loop. Okay, so let's try to give a quick comparison of that. The first is, this is open loop control system versus the uh, closed loop control system. Let's try to compare them. Okay, so the first point here is that uh, you don't have many components here because it's a straightforward only forward direction. You don't have any signal flowing back. So the construction and the design, we can simply say that everything is simple. Okay, and I can say less expensive. This is because only one way forward direction flow of a signal, and number of components you are going to use is less. That's why. Right. Yeah. So on the other side, you it will be right complicated design, complicated design, and this will be expensive. Now, whenever there is no loop, we uh, have seen that there is lesser problems related to the stability. So, right, so this is stable system, right? So here in the closed loop, we have seen that the designer should be right careful because there is a tendency of the system becoming unstable, right? So, yeah, right, designer should select the parameters such that tendency to instability is is eliminated. Okay, it gets eliminated. Then we can compare. The next feature that we can compare here is accuracy, right? How good is the output produced for a given input, right? So on the left hand side, that is open loop is less accurate. We can say that. Hmm. True. Based, correct, correct, correct. So I'll be writing that as the next point. Okay, correct. What you told is right. So this is less accurate on the right hand side. It's more accurate. Okay, great. So next one, I'll say this is right. It's not adaptive, and this side is adaptive. Right? Yeah. If you remember any points, please tell me. Okay. Then, how good is a system which is sensitive to maybe disturbance? Which one is more sensitive to the disturbance, and which one can control the disturbance? Right. So, if you see, the open loop is sensitive to the disturbance as well as the, because there is no control, right? Something changes. uh, if you give an extra input, see, a disturbance is an external input and it's additional. So if that gets added up to your input signal, the system will take that, okay, that's an input itself, let's process and give an output. So like that you get an output. There is no control over it, right? So this is sensitive to both, we can say, uh, disturbance disturbances and the environmental changes, right? So here it's insensitive to both because it has been designed in that way. Okay, now, and then let's say, what is the operating bandwidth? We have seen in, I think, maybe the network analysis where the feedback will actually increase your bandwidth. That's that concept we have studied. Okay, so because of that, open loop means it is lesser bandwidth. So here, where as soon as you generate a feedback in your uh, application, the bandwidth will be increased. So this is large operating bandwidth. So more frequencies are added to the operating range. Range increases over here. Yeah, you can consider that as information, provided as you are allowed to send more signals if it is a communication system. Okay, you are allowed to send more information because you get more frequencies added. Okay, uh, right. So okay, one more I think we can add up here related to the linearity and non-linearity of the circuit. Right? So if there is a non-linearity that is present in the system, that non-linearity will affect your output. Okay, so here the non-linearity affects the output of the system. Okay, on the other side, so the feedback will take care of that. So non-linearity does not affect the output, right? Maybe even if it affects, it's a negligible amount. Okay, so we can write uh, non-linearity does not does not affect the output. Right. So we have a lot of advantages over here, right? For using the feedback in a given system. Right. Now, then we have the concept of relation of a electric system and a mechanical system, right? Where both of them we are using the what you call as feedback, right? So because of that, we always try to represent a equation for mechanical system, and we try to convert that into the what you call as electric system. It's called as analogous system, right? So let's try to quickly try to write the representation. All right. So this is the mechanical uh, systems. So under the mechanical system, we basically have two types, because the mechanical means we are expecting some kind of motion, right? And the motion that is produced by such machines are of two categories. One is a linear motion, right? And the second one is a rotational motion, right? So the one which produces linear motion, if the mechanical system produces linear motion, this is called as translational. Okay. And if the motion is rotation, that is the system is called as a rotational system. All right. So first we will see the equational how to represent an give a equation for a translation. The translational system, we have three different elements. So every system has three elements. So the first element is called as a mass. So let's try to represent the mass in the following fashion. So mass has say two free ends. So one is denoted as A, let's say other one is denoted as B. M is the mass of the system, right? And let us say we apply force to one of the end. So say this is F of T. Force is applied, right? So in any of the mechanical system, you apply force. The response to an input, the input is a force. So the response will be in terms of motion of the object in a straight line, because this is translational system, right? Wherever you apply force, we try to denote that there is a displacement, that is x of t. So you see that f of t is more, x of t is also more, right? It's actually a linear relationship. Uh, so depending upon the mass, right, the force and the displacement can be related, right? So if you remember uh, from physics we are taking, right, how do you relate f and x using m? Can you recall? F is a force, x is a displacement. Yes, f is equal to m into a is the equation. Correct. But A can be written in terms of X itself, right? So normally I can write this is F is equal to the mass into acceleration. But we'll write now this as F of t is equal to mass is the capital M. That's what is the notation we have considered here. M into, how do you write acceleration in terms of X of t? X of t is displacement. What is the relationship between displacement and acceleration? You have equation for say displacement. Uh, how do you convert that into velocity? Velocity is displacement by time, correct? So acceleration is velocity by time. But if you consider x of t as a continuous variable, right? Then the x of t by time is nothing but differentiation, dx by dt, right? Right. So that's why you can simply write this as double differentiation, d square x of t by dt square, right? It can be measured in newtons. So that's the direct relationship for a mass, right? The input output relationship ships of mass is given by this equation, right? So the second quantity or second element that we use in uh, this translational system, it's called as a spring. Now the representation of the spring could be like this. It has two ends. Maybe this is C, this is D. Right now, if I apply, say, the force at this point, say this is f of t, right? On this side, I'm going to have xc of t as the response, right? It moves by a distance called xc of t. At the same time, the uh, spring has a characteristic that, see, if I go back to the mass, the whole mass will move by the same amount x of t, isn't it? Right? You have a mass, you keep any object on the table and apply force on one side of that body. The whole body will move by the same distance. That's why the x of t, which we have written in case of mass, is though it is written at one location, right, like this, it's actually applicable for the whole body. But you see, you consider the spring, right? Spring, yes. So the in the sense C may move more compared to the other end D, correct? So this D has a completely different movement or a completely different displacement, right? So I call that as x D of t or x1 x2 doesn't matter, right? Right. Now that means if this is the representation that we are going to give, right, then there is what the characteristic of a spring, right? What amount of displacement you find for C and what are the displacement you find for D, that is represented by a spring constant K. Now if you want to give the equation for this, then the f of t is equal to the spring constant multiplied by, this is xc of t minus xd of t. All right. So if at all we know the exact difference, if I call this itself as say x of t, right, then I can call the f of t is equal to, right, the k into x of t, where x of t is the difference. Xc minus xd of t is called as, if I call it as x of t, the complete displacement difference among them, I can put it directly over there, right? So this is the equation. Once again, we are measuring everything in terms of Newton because it's a force. All right, so let's move on to the third element, and that element is called as a damper. Okay, so the representation of damper is like this. This is one end of the damper. The representation of damper is like this. Okay, so and okay, I'll change the name for some reason because there is a damping constant coming up. That's also denoted by B. So I don't want to write a B here. So let's make this as E and F. Okay, E and F are the two ends, and the B represents the constant of damp. All right. Now, fine. So let's try to write the equation now. So again, if you apply the force to uh, one end, let's say I apply the force here. This is the force being applied, that is F of t. So we have two different movements possible. One at this side, that is connected to E. So I'll write, maybe this is displacement. So this is x E of t. Okay, and the other end will move by completely different amount. Okay, displacement at the end F is different, so I'll write xf of t. So again, this is completely different compared to the spring. So right, so maybe initially you find movement only on one side. E will move by certain amount, right? Then the F starts moving. Whereas when you consider a spring, both will move simultaneously, but amount of displacement is different. Correct. So because of that, we have to create a third object, that is a third element called damper, right? Because of these kind of movements. So now we'll directly let's write. Therefore, okay, the F of t can be equated to the damping constant multiplied by the difference of the differentiation. So this is dx E of t by dt minus dxf of t by dt. Okay, so if at all I'm able to take a difference directly as dx of t by dt, if at all I call it by this way, I can write therefore the f of t could be equal to b into dx of t by dt. Again, this is measured in newtons. All right. So these are the equations corresponding to the translational system, right? Equivalent of a translation is right on the other side, the objects which create rotational motion when you apply the force. They are called as the rotational. What is the basic difference in terms of the force of a rotational system? If you are able to recall, let me know. In terms of force, okay, we understood that the basic difference in terms of the response in the sense one will move linearly, linear system, that's a linear movement, translational. Second one is that when you apply force, the rotational system starts rotating instead of moving in a straight line. That's the difference. That's one of the basic difference. What is the other difference in terms of the force corresponding to a linear or the translational, and the force corresponding to a rotational, there is a difference. That's the basic difference. So let me know if you are able to recall that. Right, so that's a very basic difference, you are right. So we don't call it as a force. So the force is used only in case of those systems which uh, produce translational motion. Okay, so in case of a rotational system, right, it's actually the force, but since you want to differentiate by just looking at the name given, we will be able to understand that okay, which kind of system it is, right? The word force is used indicates that okay, the system is translational. As soon as we see the word torque, we will understand that okay, there is a rotational part inside this machine, and the response is in terms of rotations, RPM mostly, not the uh, displacement or acceleration, etc. So just to differentiate that, right, here we have the torque coming into picture, right? So torque generates rotation in the machine, all right, in the insert system. So the first element is called as it's not mass, equivalent of mass in a rotational system is called as inertia. Okay, correct. Okay. So inertia is J, right? We correct. So the representation slightly changes now. So we have the inertia J coming into picture. All right. So we have, instead of M it is J. So I have two ends of the machine, or the two ends of this element. So on one end, let me assume that it's a rotational force. That's why it is a torque. Okay. So this is T. And the representation of inertia is in terms of J. What is the response? So you see that previously when you applied a force F, that moved, the object was moving by a distance x. So x was the response. Now what will be the response of this system? Angle, right? So the response on, I'm going to write here is theta. Okay, theta is the response. Again, I'm not writing for side B separately, because the whole object will move by the same amount, it will rotate by the same amount. Okay, so because of, yes, the whole object will move together. There is no separate parts or something, right? There is no separation, you cannot bifurcate. So the whole object moves simultaneously as a single body, right? So at the beginning and the end of that element will rotate simultaneously, right? So because of that, now I can say that what's the response, what's the equation that we are going to write here. How the first, let me write the J is actually measured in kilograms per meter, not per, it's not per kilogram meter square. Okay, J is that. So the torque is measured, torque is Newton meter, all right. So T is equal to J into d square theta by dt square. See, there we had a d square x of t by dt square. Now it's a d square theta by dt square. So we easily we can remember by just making an analogous comparison that translational has distance or displacement, the rotational has angle, right? Hmm. Yes, j into d square, correct? Correct. So that's how we try to represent. Hmm. Yes, since the rotational motion is brought into picture, right? The appropriate terminologies have been used. All right. So force is a torque. Uh, Inertia, right, was mass earlier, and the theta was, sorry, we had the x of t, which is a displacement. Now theta is, you can call it as angular displacement. It's actually a displacement, but in terms of angle, it's angular displacement. So using this, we can directly relate the inertia to the mass. So the second one is actually another spring coming into picture, but this spring responds to the torque instead of the force. So this is another spring. So here we represent the spring in a very similar fashion. Okay, maybe this is C and D. Now you see What is the input? Input is a force, that is a torque. Torque is applied at one end. Right now, comparing this with the translational spring, the normal spring, that used to move differently at different at the its two ends. Correct. C was moving by x1 of t. The d was moved by another distance. We call that as xd of t, x2 of t, whatever. Okay. Now, very similar to that, the response of this spring to the torque has to be rotation, right? So very similar to that concept, I am going to have two different rotations, x theta c. So xc was there, I'm replacing it with the theta c because it is rotational. The other end moves by a different angle, so let's denote that as theta d. So once again we have a spring constant k here, but this k actually controls the amount of rotation, right, not the amount of linear motion. So when I say that this is the amount of rotation, I should be able to write an equation for torque in the same fashion like we did earlier. So the F was equal to, true, true, true. Yes, yes, right. How much, how much theta, how much angle, how much, by what angle C gets rotated and by what angle D gets rotated. They are different. That's why, right, there could be a bending effect. So this is, we wrote x1 of t minus x2 of t there, right? So x1, x2 is are getting replaced by theta now. So this is theta C minus theta D. So, right, this is the equation. If you can represent theta c minus theta d as some theta, right, the actual difference between them, you can also write t as k into theta over here, right? Other representation. So the k is actually measured in, this is Newton, and the radian goes to the denominator. When theta goes to other side, that is capital T by theta. So capital T is measured in terms of Newton meter torque, right? So this is Newton meter per radian is the unit for K, right? So the third one is the damper, right? So the difference here is nothing but it's a rotational damper. So we still consider the damper, right? And the damping coefficient we call it as B, right? We have, say, this is side E, this is the end F, and one end you generate the torque, and we know that two different responses will come. So this is theta E, and other side rotates by theta F, right? There will be a difference between the spring and the damper like the translational case, right? Maybe theta E will start rotating initially, right? Right. After that damping gets over, theta F also starts rotating at a different after some time. So there is a difference. So in case of a spring, both will get both start rotating simultaneously, but the amount is different. Amount of rotation is different for two ends of a spring. So because of that, now let's write the equation. So torque in this case is equal to the constant B into, if you remember, for a translational motion, we wrote it as dx1 of t by dt minus dx2 by dt, correct? So similarly, now the first we'll write, that is d theta e by dt minus d theta f by dt. So we will call this difference as some d theta by dt. Then we can write T is equal to, torque is the uh, coefficient of This is also called as a viscous friction. Okay, uh, d is called as a coefficient of viscous friction, anyway, into d theta by dt, right? So the b is measured in terms of the newton meter per radian per second. Okay, because d theta by dt will go to the other side. So t is in newton meter divided by d theta by dt. D theta by dt is, theta is radians, time is second. So that's why the equation, this is measured in terms of this. Are you okay? So fine. Now let's try to represent, how do you represent a mechanical system is very important now, right? So let's solve a problem quickly just to recall the concept. Okay, then you can build up the different systems, and you can convert the systems into the equations using the same procedure. All right, so for so this is the system, and we want the find the transfer function could be the question here. All right, for any given mechanical system also we should be able to write the uh, equations first and convert the equation into the transfer function. This is what is the required target now. So let us consider we have the following system. Okay, so mass m1, m2, say this is spring k1, damper b1, and this is the force that is being applied, f of t. So there is displacement x1, and there is another displacement marked over here as x2. Okay, so let me see, the question here is to find out the transfer function. All right, so obviously this has to be a ratio output by input. So from the given diagram, we can understand that the input will be f of t, force is the input. But you see that we have two outputs possible, correct? X1 is one, X2 is the second one, right? Two displacements possible. So now the question is which one to consider for calculation of the transfer function, right? So there is another version of the same statement which I made now. So what if the X1 and X2 are not given, right? So consider that the diagram is just this part, right? I have only this part given. Okay, no displacements marked over there. Then what to do, right? That's also has the same answer. Okay, so let's assume that that's the case. The x1 and x2 are not marked, right? So what you do, wherever you see a mass, right, you generate corresponding displacements, because we know that the whole body of the mass will move by the same amount. I cannot do this for a B or K or anything else, right? I cannot do that because it's two ends will, both the ends will move by different amounts. So what you do, you mark, if x1 x2 displacements are not marked, then this is the idea. Okay, wherever you see the mass over there, simply write one displacements, give x1 x2 x3 as required. Okay, so that's the first point. So that makes sense now. Already they have given in the same fashion. Wherever you see m1 m2, they have marked x1 and x2, right? So first problem is solved. Second one is that this could be something like you are applying an input, and you get two outputs possible, like x1 and x2. If you want to find the transfer functions, right, recall what we used to do in circuits, right? Uh, think that this f of t is a voltage that is being applied. Okay, voltage you apply, you get say two currents in the circuit, x1 and x2. When I apply certain amount of voltage to a circuit, I might get that there may be two different loops or something, right? Yeah, so you have two different connects, right? For calculating the gain, or these x1 x2 could be two different voltages also. I apply a voltage at the input, I have two different voltages being produced inside my circuit, right? To calculate the gain, you always use the final one, right? Like the output voltage by the input voltage. In that sense, you will make sure that this is a intermediate voltage. This is the intermediate, what you call, response, intermediate output. I don't want that. I want always the final output. So final output by the input, that is f of t. Okay, so you use, in that way you find out what could be the final result, divide that by the input. So final result is this, input is this, so x2 by f is what I want. All right, so the question is, in that sense, so find the transfer function means you are going to find out x2 by f, output by input. That ratio has to be found. All right. Okay, so let's write the equations. So the easiest way is to convert this given diagram, right, into an equivalent diagram. We try to write a network for this, right? Convert this given mechanical system into something like a circuit. Okay, it's not exactly a circuit, but we try to represent in terms of the network, right? So always you write equivalent network. Right. So how to write the equivalent network? That's also pretty straightforward. We have to simply follow one rule. Mark the responses and the inputs. Okay. First. So that means x1 and x2, what we see are the responses. As I told, you can relate it to the intermediate voltage that is being produced in a circuit. So intermediate voltage you always measure at a node, right, in a circuit. So see, x1 is a node, x2 is another node, right? Directly start from here, x1 and x2 you mark. Now what and all components are connected and what and all inputs are provided with respect to x1 you mark, right? So I can see that x1 is connected to p1, k1, m1 and k2, and input is provided to that. So let's write that now. So I can see that the M, B1 and K1 are directly connected to this in the following fashion. So yes, yes. So if correct, correct. So see, this three correspond to the K1, B1 and M1. Okay. The K2 I am not writing here. K2 is between X1 and X2. Correct? Write only the K2 between X1 and X2. Others are directly connected to X1 itself. So you see this is the I think M1. The spring is connected. See, there is a reference point, right? On the top, you can see that this is a reference, right? So anything connected to reference in our circuit, what is the reference? It's a ground, right? So that's why I'm connecting K1, B1 and M1 to the ground. This is the ground, right? This is the reference. So this is K1, this is B1. Okay. At the same time, I can see that there is an input f of t, right? The input f of t is also connected to this. So here itself I connect. Maybe you can show it as a voltage or current, doesn't matter. Okay. This is also being applied to the same point x1, right? So this is the input. So I think input is denoted as f of t over there. So I'll write the f of t itself here. Okay. Then go to x2 and see what is everything connected to x1 is over. So I'll move to x2 now. So and m2. So out of which k2 is here, correct? Between x1 and x2, this is k2, and m2 is only connected to k2, correct? So that means M2 is only connected to X2. Sorry. So that means you will write the M2 between this and the reference. So this part actually completes our what you call the required equivalent network conversion of the given system into the network. All right. Now what we do first, let's write the equations, right? The relationship between the inputs and outputs at each node. This is our first target. So at node x1. So let us, yeah, it's similar to the circuit analysis. Whatever is the input and what is the output, I'll write. So at x1, I can see that there is a mass m1 d square, because this is the equation we wrote earlier. What is the force applied on a mass? What is the response? It is m into acceleration. Acceleration is d square x1 by dt square. Plus, what is the response of the b1? b1 is nothing but b1 dx1 by dt, isn't it? Plus, there is a k, so k1 into x1. But also, I can see that x1 and x2 is connected through another spring of constant k2. K2 has two different motions, so that will be x1 minus x2. This is equal to the force F of t. Yes, that will be considered as positive, and the other node will be negative. Okay. Right. Similarly, let's write an equation at x2 now. So at x2, right, what happens? So there is one mass, so that will be m2, and the displacement is x2. So d square x2 by dt square, plus again k2 comes into picture. Now the x2 is positive, x2 minus x1, right, is equal to, yeah, can you tell me what is there on the right hand side here? Yes, on the right hand side. See the above previous equation. At x1, I wrote f of t. No, no. Previous equation, it was f of t because there was an input being provided. Zero. So no input. So this has to be zero. Okay. So input is equal to output, but there is no separate input being provided. Okay. So input is equal to zero, but there is an output coming up. That's something very simple to our mesh analysis. One side you have a voltage. Because of that, some current will flow in other part of the circuit. Same thing. Similar reason. So you have equation at x2, node x2, written in the following fashion.